Hello, hello, and welcome back to your Topic 3 on Power Series in AP Calculus BC. Day 41 today, we're going to go over compositions and combinations of power series. Really, this is going to take everything you already know and just see how we can be a little bit more efficient with power series. So let's begin. There's an opener here that I'd like you to try on your own, and then once you've tried them, we can come back together. So good luck with all four of these. It does find the power series. That's pretty poor directions. Really, it means write the Maclaurin series. Right? And probably spell better than I did. There we go. The Maclaurin series for each one. Ready, set, go. All right, and we're back. We probably should have ended up with something. We know this one. This is our geometric power series. Really easy to write, yeah. We can get that general term in there as well. And then g of x, once you go through all the work, because this is not one of the ones we're used to, it probably won't shock you too much, I think, that your power series ends up like this, with a general term with an extra 2. Nifty. So how do the two power series compare to each other? And is there a shortcut that would make them faster, finding them faster? Well, hopefully yes. In fact, my guess is you probably use the shortcut on problem 2, which is just fine. You'll notice that we could think of g of x as 2 times 1 divided by 1 minus x. So 2 times 1 plus x squared, all the way up to that general term, right? And then you multiply it out and end up getting g of x over here. Now, we didn't do the interval of convergence yet, so we should probably think about that. The interval of convergence is actually a pretty easy one. Because this is geometric and the sum of a geometric series only exists if your common ratio is less than 1, strictly less than 1, can't be equal to 1 because then you're just adding 1 every time. And we know that this is x, right? X is our common ratio. We multiply times x every time. Then really they're telling us that our x has to be strictly less than 1. And look, oh hey, that's the result of the ratio test. Very exciting. And when you go through and work it out, you end up getting this guy. Testing the endpoints will show you that neither endpoint works. If you replace x with -1, then you go 1 minus 1 plus 1 minus 1. It doesn't add up to anything. When you replace x with 1, it becomes 1 plus 1 plus 1 plus 1. It adds up to infinity. This guy's a little bit trickier. Maybe we should go through and actually try the ratio test here and see how we do. So if we do the ratio test really quickly, nothing too terrible, right? I guess we should probably write this in summation notation, huh? So it is the sum from n equals 0 to infinity of 2x to the n. So when we do the ratio test, absolute value, we get 2x to the n plus 1 divided by 2x to the n. And then simplifying a little bit more, zooming in so we can actually see this, you should notice that the 2's cancel out, and we get x to the n times x to the first over x to the n. Those cancel. There's no n's left now. So I think we really are just left with x, and we know that as the result of the ratio test, that better be less than 1. So you actually get the same interval of convergence. And that really should not surprise us too much, because we've talked before about how a constant multiplying in doesn't change the convergence of a series. And it turns out it doesn't change the interval either. So our interval, again, is that x needs to be between -1 and 1. Is there a shortcut to go between these two? Well, sure, it's the same interval of convergence. Easy shortcut. Now, one of the reasons power series are so powerful, pun intended, is that as soon as you know one of these parent power series, and we've memorized 4, right? E to the x, sine, cosine, and 1 over 1 minus x, you can generate many, an infinite number of other power series with very little effort. There are 4 rules that we're going to have to keep in mind, and we're going to kind of expand on those as we go through. So I'm going to discuss 2 different power series. I'm going to discuss f of x, where the power series, or rather f of x, is represented by this power series. And then we're going to talk about g of x, which is represented by the power series that I'm doing over here. So these are 2 different functions. Maybe this is e to the x and this is sine of x, something like that. 2 different functions. Well, the first rule is essentially multiplying a power series by x to some power. Okay, let's maybe look at the example first, and then we can work backwards from there. So if you are asked to create the power series that represents f of x equals x to the fifth divided by 1 minus x, what do you do? Well, I always break it down into two pieces, or as many pieces as necessary. I start with the power series I know, which is 1 divided by 1 minus x. And we've seen this one, a couple times even so far today. Always good to include that general term, because normally these problems ask for the new general term as well. Then I say, well, how do we turn this into our new power series? Well, we do that by saying this is the same power series, but multiplied by x to the fifth. That was supposed to be in a different color. Awkward. There we go. And so, working to the right over here, we get x to the fifth, which multiplies times 1 plus x squared plus x cubed. I usually go out about 4 terms before putting the general term, but it's up to you. The problem will tell you what to do. And then we need to realize that this guy is our definition of f of x. So we can say that f of x equals, distribute that x to the fifth, add our exponents here, x to the 8th, plus add our exponents, so x to the n plus 5. And there we go. We have created the power series with very little effort for this guy. Now, could you go the long way around? Could you take the derivatives and work with f of 0 divided by 0 factorial over x minus 0 to the 0th, and so on and so forth? Well, of course you could. However, which way was faster? Hopefully you're saying, oh yeah, this way is way faster. And it is. So, moving to the left, if you have one power series multiplied by x to the m power, where here's my x to the m power, the resulting series will converge to the original function, just multiplied by x to the m. And don't forget to distribute that to all of the terms. So saying that, we multiply x to the m times the power series, and it's equal to x to the m times the original function. Nothing too terrible. Now, one thing to note. We are allowed to use these two properties here as long as we're not changing the center, right? Technically, all of these are x minus 0 to the fifth, x minus 0 to the sixth, and same thing up here, right? These are also x minus zeros. So both of these are still centered at 0. The original is Maclaurin, the new is Maclaurin. But what you're going to find is sometimes, especially on our compositions, which we're going to see down here, if you compose a value into your power series that changes the center, then you will still have a power series, but you're no longer going to have a power series centered where you may have wanted it. And we'll see an example of this in just a second too. So our second rule then is you are allowed to compose, or maybe you think substitute, x to some power into a power series. All right, well, what does that look like? 1 divided by 1 plus x squared. Well, I think we can start with our same geometric power series again. Something like this. Okay, and then how do we turn the denominator into this guy? Well, I think we can keep everything the same, except instead of x, we can compose minus x squared, negative x squared in here. And then if you distribute the negative, it becomes positive. The square is not acting on the negative. The square is just stuck to the x there. And so what does this composition look like? Well, I like to rewrite the same series above, running a bit out of room here, sorry, but replacing all the x's with our composition. We're going to replace every x with negative x squared. All right, and then we can see as we simplify this down, this becomes 1 over 1 plus x squared. And then we get 1 minus x squared. And then this square is acting upon the entire thing. And when you square a negative, it becomes a positive. So x to the fourth minus x to the sixth, and then plus, and so on and so forth. Now, this guy at the end is a little trickier, right? Because this n power, if it's odd, will cause the negative to stay. But if it's even, it will cause the negative to go away. So we're alternating in sign, which I think means we're actually going to add an extra -1 to the n here. But then we still have to multiply these together, so it really becomes x to the 2n. And double checking really quickly, if I replace n with 0, and by the way, we always assume that a power series starts at the 0th term. If you want it to start at a different term, that's fine. Just make sure you're extremely clear about where you're starting. So this started at the 0th term unless you wanted to start at the first term or second term, and then your general term changes. So if we try n equals 0 here, that becomes 0. If this is 0, that becomes positive, and we get positive 1. That looks good. N equals 1. All right, this is x to the 2nx squared, that's that guy. And then n negative 1 to the n is a negative, that's that guy. That works out well. Yeah, I think our formula here looks pretty darn good. That's all this composition is saying. It's saying you can replace the x in your formula with another function. But again, we need to be very careful, because if we replaced our x over here with something like x minus 1, then you would have a new power series, but the power series would not be centered at 0 anymore. The new power series would be centered at 1. So if they said, how can you create a power series centered at 1? You'd say, oh, we just substitute in x minus 1, and now we've shifted our center, and that's totally fine. All right, these last two properties can be used for any function of x, and you can have things like x plus 1 or x minus 3. You're not going to change the center with this one, because what you're doing here is you're saying, well, if you have two power series and you add them together, it does actually create a result of two functions added together. And so showing this very quickly, if you have h of x equals e to the x plus cosine of x, I start with the individual components. E to the x, we hopefully remember 1 plus x squared over 2 factorial, x cubed over 3 factorial, and so on and so forth. And then cosine of x is an even function, so we have even exponents starting with 0, and we always alternate in sign with our two trig functions, like so, and so on and so forth. There are those two, but if we wanted to create h of x, wrong color, is created by adding those two together. And that's where things get a little bit tricky here. So when we add these together, and I'll give you some hints, it needs to be e to the x, so 1 plus x squared over 2 factorial, plus x cubed over 3 factorial, and so on and so forth, right? But then added, I should zoom in here, to cosine of x. So x to the 0th over 0 factorial, let's rewrite that as 1, no reason not to, minus x squared over 2 factorial, x to the 4th over 4 factorial, and so on and so forth. Okay, but this asked us to list the first 4 non-zero terms. And so whenever you're combining multiple functions together, you are required to simplify this down so that you can see the coefficient attached to each power of x. So right now I have, for example, well, we should probably just do this together, like terms of 1 plus another 1, which is certainly 2. We took care of those. I always cross them off once I've done it. Then we have just x to the first. There's no x to the first over here. So we have this x. There are two terms, but they want the first 4 non-zero terms. Okay, we took care of the x. Then we have x squared over 2 minus x squared over 2. Those guys cancel each other out. The next one is going to be x cubed. Okay, nothing too bad there. So the next one is plus, keep green, plus x cubed over 3 factorial. But then I have another term, and you're like, oh, it's just x to the 4th, that's easy. Well, actually, even though we only wrote the first 4 terms here because one of them canceled out, we actually need to include another term. We need to include x to the 4th over 4 factorial. Right, and notice that we have 2 of these here. So if you want to be really lazy on this, and I'd suggest you do be lazy, I'm going to take the coefficient from the first one, which is 1 over 4 factorial, and then add it to the coefficient of the other one, which is also 1 over 4 factorial, and say both of those are multiplying by x to the 4th. And when you group like this, and you can put another plus after if you would like, when you group like this, you're showing the coefficient of x to the 4th. That's not a simplified coefficient, but you do have to show what's multiplying by x to the 4th. Now, someone might say, well, wait, can't you simplify that down a bit? And yes, of course you can. You could have written this, 1 plus 1 is 2, as 2x to the 4th over 4 factorial. That's totally fine. However, this oftentimes is a lot faster, and you'll see that I do that on my solutions. All right, last but not least, if you have two power series multiplied together, the resulting series will converge to the multiplication of the functions. So if they're asking you to find the power series for two functions multiplying together, you can certainly find the individual power series and multiply them. But this is really tricky. And we might want to see why it's tricky in just a second. So let's start with our two functions here. We're going to do cosine of x, which we've already done. They want p sub 3 of x. They want the third degree polynomial, so out to the third power. So I know I'm probably only going to have to go out to the third power here. So let's take a look. X to the 0th, 0 factorial, x squared over 2. And we can go to x to the 4th, but that's going to be too big. And I doubt the power is going to get reduced. So I'm probably just going to go that far. And sine of x to the 1st over 1 factorial minus x cubed. I bet I can probably stop here. However, let's go one more just for fun. Okay, and this should be a minus. Apologies. Great. So how do we find f of x? Well, f of x is found by taking cosine of x, and maybe I should write this as 1 minus x squared over 2 factorial plus whatever else. I don't think I'll need anything else. And then sine. X, just x I think is fine, minus x cubed over 3 factorial, and I shouldn't need anything else. Now how do I multiply all this? Well, I do need to multiply every term by everything else. This is, think distributing, right? This one's pretty easy. I need to distribute the 1 to both of these. 1 times x is x, and 1 times x cubed is x cubed, still with that 3 factorial. But then we need to distribute the next guy, and this becomes minus x cubed over 2 factorial. Right? And then this one you could multiply, but x squared times x cubed is x to the 5th, and that's too big. We don't need that because we just want the third degree. So I think actually that's as far as we need. But this would not get you full credit because you haven't grouped the coefficients of like terms together. So we would have to write this as x, and I always put a plus here, and then take the two coefficients, negative 1 over 3 factorial minus 1 over 2 factorial, and group it next to x cubed. So that way you can see your two coefficients here, and then you're fine. Again, you could group these together. You could say that's negative 5, 6, or whatever it ends up being. I think that's right. No, not quite. Negative 4, 6, I guess. Either way, you could group all those together, and you could continue to simplify it down, but this is fine. But with series, you do have to show one, we'll call it a unified coefficient in front of x cubed. You would not be able to leave it like this. All right. A few concluding notes. Any substitution into a Taylor series that results in a Taylor series is allowed. However, and I mentioned this earlier, beware because your center may change. For example, a few years ago, there was a great question. It asked students on the AP exam. It asked students to write the Taylor series for the polynomial this, centered at the origin. And so what a lot of students did, and this was fine, it was very, very clever of them, ultimately ended up not working, so I guess it wasn't fine, is they started with sine of x. And they said, okay, sine of x, that's going to be, okay, we just did this one, x to the 1st over 1 factorial. Cool. And we won't do too many terms. We'll do 4 terms here, I think. And so on and so forth. And then they said, okay, we're just going to replace all the x's with 5x plus pi over 4. So they said sine of 5x plus pi over 4. And they started replacing them. So they said, well, this is x over 1, so this just becomes 5x plus pi over 4 minus, and then they took the next one, 5x plus pi over 4 cubed over 3 factorial. And then the next one, and you get the idea, right? I don't think I need to do another one after this. And so on and so forth. This is a power series, but it is not the power series for this centered at the origin. Why is it not centered at the origin? Well, look at this. We can see that this is not centered at the origin. If you manipulate 5x plus pi over 4 to the 5th, or whatever power you wanted to manipulate it to, you can factor out a 5 from both of these, right? If we factor out a 5, it becomes 5 times x plus pi over 20 to the 5th. Or you could rewrite this 5 to the 5th is some huge number, but it becomes 5 to the 5th times x plus pi over 20 to the 5th. This series is centered at x equals negative pi over 20. So just by manipulating that, you'll be able to see that every single time that it's centered at negative pi over 20. And that did not do what the problem asked. The problem asked for the polynomial centered at the origin. So for something like this, where they're giving you a function that when you compose it causes the center to change, you would have to go back to your original. You'd have to find y. You'd have to find y prime. You'd have to find y double prime of all these. And then you'd have to evaluate each of them at 0, and then you'd follow your usual pattern for creating a Taylor polynomial. So don't forget that although we do know our power series formulas, our parent series, if you will, if they ask you to do something that changes the center, you do have to go back to your original general form for a Taylor series. As a heads up, substitutions have the following effect. If you substitute in x minus c, it will of course translate the center of your series. If you compose a times x inside, right, it is going to change the radius of convergence, assuming your original radius was finite. Right, and so that's different than what we did on the opener, because you might have said, well, wait, it didn't change here. You didn't substitute in 2. Here, you multiplied by 2. Substituting in 2 might have been something like you replace x with 2x. That would double your radius. All right. What else is interesting? And then ax minus c changes both the radius and the center, and that's because you can factor out a to write it like this, and you can see the radius will change and the center will change. This is really beyond the AP exam, but it's nice to know. And then last but not least, Taylor series are unique. There are many ways to find a Taylor series, but every way you find a Taylor series for a function that is centered at a given point, they will all simplify down the same way. So again, giving an example, if let's do this guy over here. If you didn't think to do it this way, and you said, no, I'm just going to rewrite this. This is 1 plus x squared to the negative first, and then I'm going to find g prime, and then I'm going to find g double prime, right? And you just do that general Taylor series formula. Eventually, you will get the exact same Taylor series. You have to, because they are unique, centered at each point. Okay, well, that's really all for now. You guys have a bunch of practice AP problems. I just cherry-picked various questions out of the AP exam. You'll notice, though, that every single one of them is from problem 6 on the BC exams, on past BC exams. And that's because problem 6 is always, always, always the series question. It's generally on power series, and it might incorporate some of our series convergence tests. But problem 6 for the last 15 years now has always been power series. Okay, what does that mean, always been power series? Well, the AP exam is set up for BC, where 3 of the problems on the free response out of your 6, 3 of them are on AB material. Nothing new that we've learned this year. The other 3 are all about BC. You need to know BC to get through all 3 of them, even though they might incorporate some AB stuff. And out of those 3, the 6th one is always power series, which means a third of your FRQs for your BC score comes from power series. That's why we spent so long on it, almost 2/3 of the first semester, and that's why we're going to practice it a bunch next semester. So here is your practice. I already have the answers uploaded on Teams if you'd like to check them. You can always Google. These are all non-secured exams. So if you look up 2015 Problem 6 BC exam, you will find the solution keys for these as well. Thank you as always for working so hard, and I'm excited to have you back next class. We only have a couple classes left for this semester.